fundamental nature of reality is? Welcome, travelers, to a place where reality seems to lose its meaning, a place that challenges our deepest understanding of the world as we know it. This is the quantum realm, a world of subatomic particles where the laws of classical physics no longer apply. In this realm, particles like electrons, protons, and quarks perform a strange dance. They can exist in multiple places at once, spin in two directions simultaneously, or even affect each other's state from vast distances. These peculiar behaviors are not just curiosities, they are the backbone of quantum mechanics, a theory that underpins the fabric of our universe. Quantum mechanics is a realm of probabilities, not certainties. Here, particles don't have definite properties until we measure them. Before measurement, they exist in a superposition of states, a blend of all potential outcomes. It's like they're playing hide and seek with us, refusing to reveal their true nature until we look directly at them. But the strangeness doesn't stop there. Quantum mechanics also tells us that particles can be both particles and waves at the same time. This wave-particle duality is another cornerstone of the quantum world, further straining our understanding of reality. These quantum quirks may sound far removed from our everyday life, but they have startling implications. Our computers, smartphones, even the sun that warms our planet, all owe their existence to the bizarre rules of quantum mechanics. While this journey may be filled with uncertainty and paradoxes, it is also one of discovery and enlightenment. As we delve deeper into the quantum realm, we find not just weird particles, but a whole new way of thinking about the universe and our place in it. So buckle up and put on your thinking caps. We're about to embark on a journey that will bend your mind and challenge your understanding of reality. Now prepare to delve deeper into this realm of uncertainty and probability. In the quantum world, things can be in two places at once. It's a sentence that defies our everyday understanding of reality, but welcome to the mind-bending principles of quantum superposition and wave-particle duality. Let's start with the principle of superposition. In the quantum realm, particles don't have definite states, instead they exist in all possible states at once, until they're observed. Think of it like an unopened box containing Schrödinger's famous feline, simultaneously alive and dead until someone peeks inside. This isn't just theoretical musing, it's a fundamental principle that underpins the quantum world. But how does a particle decide which state to choose when observed? Well, it doesn't. The act of observing actually influences the outcome. It's a concept that continues to puzzle and fascinate scientists, and it's a cornerstone of quantum mechanics. Now let's shift gears to wave-particle duality. This is another quantum oddity that has left scientists scratching their heads. You see, particles such as electrons and photons can behave both as particles with a definite location and as waves spread out over space. This was famously demonstrated in the double-slit experiment, where particles shot at a barrier with two slits didn't just go through one slit or the other, but somehow through both at the same time, creating a wave-like interference pattern on the other side. When observed, however, they behaved like particles again, passing through one slit or the other, but not both. It's a concept that challenges our understanding of reality. How can something be both a particle and a wave? Yet this is exactly what quantum mechanics tells us. It's not about the particle or the wave, it's about the particle and the wave. So, as strange as it seems, particles can behave both as particles and waves. Welcome to the wonderfully weird world of quantum mechanics, where the impossible becomes possible. And imagine two particles that are instantly connected, no matter how far apart they are. This isn't the plot of a science fiction movie, it's a real-life phenomenon known as quantum entanglement. In the early 20th century, scientists began to observe that pairs of particles could become entangled in such a way that their properties become intimately linked. What's even more intriguing is that this connection persists regardless of the distance separating these particles. Whether they are a few millimeters apart or on opposite ends of the universe, changing the state of one particle will instantly change the state of its entangled partner. This concept was so strange, even to the pioneers of quantum theory, that Albert Einstein, Boris Podolsky, and Nathan Rosen proposed a thought experiment in 1935 to challenge it. Known as the Einstein-Podolsky-Rosen paradox, it argued that quantum mechanics must be incomplete because it allows for what Einstein called spooky action at a distance. Einstein believed that the physical realities of the universe shouldn't depend on the observer, and this entanglement seemed to contradict that. However, in the late 60s, physicist John Bell formulated a theorem that showed the EPR paradox didn't disprove quantum mechanics, but rather highlighted its inherent weirdness. Bell's theorem demonstrated that if the universe obeys local realism, the idea that the physical world exists independently of our observations and that information cannot travel faster than light, then certain statistical properties of entangled particles would be limited in a specific way. But experiments have shown that these limits are violated, meaning the universe is either non-local or non-realistic, or perhaps a bit of both. In other words, the universe might be even stranger than Einstein thought. Quantum entanglement isn't just a quirky detail of quantum mechanics, it's fundamental to the whole theory. It's a clear demonstration that the quantum world doesn't play by our everyday rules. This spooky action at a distance truly showcases the non-local nature of quantum mechanics. Scene script. Ever thought of walking through walls? In the quantum world, that's possible. Imagine you're a tiny subatomic particle, a teeny speck in the grand universe. You're racing towards a wall, but instead of crashing into it, you simply pass through as if it wasn't even there. Welcome to the concept of quantum tunneling. Quantum tunneling is a phenomenon that defies our everyday understanding of the world. In classical physics, if a ball doesn't have enough energy to roll over a hill, it won't make it. The same should apply to a particle trying to cross an energy barrier. But in the quantum realm, rules are slightly different. Even if a particle doesn't have enough energy to cross the barrier, there's a small chance it can still make it to the other side. This isn't due to a sudden burst of energy or a magical power, but rather, it's a consequence of the dual particle-wave nature of quantum entities. The particle doesn't go over the barrier or around it, but it tunnels through it, hence the name quantum tunneling. This phenomenon isn't just a theoretical curiosity, it's a fundamental principle that underpins many technologies we use today. For instance, tunneling is crucial for the operation of quantum computers, a technology that promises to revolutionize our world. It's also fundamental to the workings of the sun, where particles tunnel through energy barriers to undergo nuclear fusion, producing the heat and light that sustains life on Earth. Quantum tunneling also plays a vital role in scanning tunneling microscopes, allowing scientists to view the world at the atomic level, and in flash memory devices like the one in your smartphone. In fact, without quantum tunneling, our modern world would look very different. So, while walking through walls may not be on the cards for us humans just yet, in the quantum world it's business as usual. And the effects of this bizarre phenomenon ripple through our daily lives in ways we might not even realize. Quantum tunneling thus opens up a realm of possibilities that were once thought impossible. How does this quantum weirdness apply to our everyday world, you might ask? Well, buckle up, because we're about to explore the curious connection between the quantum realm and our macroscopic reality. In the grand scheme of things, the quantum world might seem distant, abstract, perhaps even irrelevant to our daily lives. But oh, how appearances can deceive. The truth is, the quantum world is not just a phenomenon occurring in some remote corner of the universe. Instead, it's happening right here, right now, all around us and within us. Let's take a moment to ponder the Copenhagen interpretation, one of the most widely accepted theories explaining quantum mechanics. According to this interpretation, a quantum particle exists in all possible states simultaneously, only collapsing into one state when it's observed or measured. This might sound far-fetched, but it's this very principle that allows for the existence of lasers, superconductors, and even the transistors that power your computer and smartphone. Then there's the many worlds interpretation, an equally mind-boggling theory. It proposes that every time a quantum decision is made, reality splits, creating a new parallel universe for each possible outcome. So in some alternate reality, you might be a quantum physicist, a rock star, or even the president. These theories, as abstract as they might seem, are not just philosophical musings. They have real-world implications, influencing the development of quantum technologies like quantum computers, which promise to revolutionize everything from medicine to encryption. But perhaps most importantly, these quantum phenomena remind us of the fundamental interconnectedness of our universe. They challenge us to rethink our assumptions about reality, nudging us towards a more holistic understanding of the cosmos. We're only scratching the surface here. The quantum world is a vast, uncharted territory, filled with countless mysteries waiting to be unraveled. And as we delve deeper, we're sure to uncover more of its profound implications for our reality. So the quantum realm, with all its oddities, shapes our reality in ways we are only beginning to understand.